All right, we're back. We're on page 2 of note 6. We're talking about direct comparison, and what we want to do is see if these series converge or diverge using the direct comparison test. So the way we want to do that is we look at it. Basically, you look at, so how I do these, let me say, is I look at them and I say, like, basically, what is this series? So if nothing had happened, if no bad things or good things had happened to each term in the denominator would have really just been it would have really just been from 1 to infinity of 1 over, I mean, n is just n. Why are we adding 1 to this other n? So like just n. And why are we adding 2? Just n, right? So this looks a lot like just 1 over n cubed to me. But things have happened to it, right? So now the question is the given series that we're trying to talk about, is it bigger than 1 over n cubed, which would be useless to me? Or is it smaller than 1 over n cubed, which would be very useful because 1 over n cubed converges p series where p is equal to 3, which is greater than 1. So that's my goal, is to show that the original is smaller than the one I'm comparing it to. That's what so you need to bring your series to this comparison, right? So you're going to use geometric series, you're going to use p series. Those are the main weapons that you have because you know what those are doing. So we try to find one of those that looks like the thing we're given, and then we work with it. So let's see how this goes here. So I'm going to say for n greater than or equal to 1, n times n plus 1 times n plus 2 is definitely greater than or equal to n times n, which is n cubed. And then I'm going to take reciprocals. So 1 over n plus 1, n plus 2. That's going to flip the sign 1 over n cubed. So let's say therefore. And also this is greater than 0. So let me move that over a little bit and just say greater than or equal to 0. I mean, it's definitely greater than 0, but whatever. Positive term series. Let's get rid of it. It's just greater. Okay, so greater than 0. So now we're trapped, right? You're trapped between 0 and 1 over n cubed. 1 over n cubed converges. So let's say since 1 to infinity, 1 over n cubed converges, p is equal to 3, which is greater than 1. We know that the other series, 1 over n, n plus 1, n plus 2, converges by direct comparison. And that's like, I mean, that's all it takes. And it's pretty satisfying. Like it's a fun test to use because it feels very very assertive, right? Like you're like, you have no choice. You have to converge. The challenge becomes, is the thing that you're going to try to compare it to, is it on the right side, right? So here I have 1 over root 2n minus 1. So that's not a normal looking thing, but it kind of looks to me, sorry, had the wrong tool there. It kind of looks to me like, can't do it, whatever. N is 1 to infinity. It looks like if nothing had happened to it, maybe just this, maybe. So what can we do? Well, I need to know if 2n minus 1 is bigger than n, basically. Because if it's bigger than n, then when I subtract it, we're good. When I reciprocate it, when I take the reciprocal, we're good. So let's see. For n greater than or equal to 1, is root 2n minus 1 greater than or equal to root n? I actually need it to be less than, because I want it to be greater than, okay, problem, but maybe not a problem. So here's what I'm going to do. Let's ignore everything that I said, pretty much. I'm going to leave that 4 part. I'm going to do something weird-ish, or I'm going to say that something weird happened to this, but like not the worst thing in the world. Let's say this. Let's compare it to this, because this is really just 1 over root 2 times 1 over root n, which is really just 1 over root 2. So this is an example of how I often stumble. You know, I think I know what I'm doing, and then it turns out it's not useful. So this is a p-series with p equals 1/2. This diverges, right? So if, is this going to work? Is this not going to work? So that is bigger, which means that's smaller, so that's bigger. So yeah, okay, I think we're good. Let's see. Let's just do it. I'm like overthinking this. All right, so here we go. Let's try this. 2n minus 1 is definitely less than or equal to 2n. All right, that's good. Got something on my screen there. Now, since they're positive, the square roots, positives and greater than 1, this is true. Okay, so that's true. And then if I take the reciprocal, then it's going to switch. And it's like, is that what I even want? Yeah, it is in this case. Okay, good. Whoo. All right, now, so we got this. So since the sum of 1 over root 2n is equal to is equal to 1 over root 2. I'm going to take that out, and then n equals 1 over n to the 1/2 diverges, and so that's with p equals 1/2, which is less than 1. All right, so the smaller series, each term is smaller. The smaller one diverges, that means the bigger one has to diverge. So we got there eventually. So since this is true, the sum of 1 over, which kind of like my personal struggle with this, I think illustrates the trickiness of the direct comparison test. So for example, if it had been radical 2n plus 1, this whole argument would be out. Like it just wouldn't have worked, and we'd have to come up with something else. So in this case, it worked for us, but it was, it was not super obvious. I'm gonna do one more, and then come back in the next video and finish this up. This one's gonna go better. I can feel it already, because this one's pretty more straightforward, I think. All right, so for n greater than or equal to 1, 2 plus 3 to the n has to be greater than or equal to just 3 to the n. And this, like, it basically looks geometric to me, like with some like shift happening, which means I'm going to try to compare it to a geometric. And it only works if it works. So this is the key step, where do you get the relationship you were hoping for? Which we do, because we know that the sum of 1 over 3 to the n converges, geometric, r equals 1/3. Therefore, the smaller series, which I'm going to say is also greater than 0, the smaller series must also converge. So this one went as well as I wish the last one had. So since, what are we going, 1 to infinity? Yes, we are. Of 1 over 3 to the n converges. And I'm going to say it's geometric. R equals 1/3, which is less than 1. Since that converges, we know that 1 over 2 plus 3 to the n converges as well. So, I mean, do you feel like you're doing anything? Not really, which is like the weird thing. You do all these series tests, and it's like, it's pretty nice. It's fun to like do a problem and get it right, but like we're not finding the sum. We're just saying the sum does exist. Will we ever find the sum for this? We won't. We do know it exists though. So like we can approximate it. Use 1,000 terms, use 10,000, use 1,000,000,000 terms, whatever you want. It's worth doing because this definitely converges. So we can start thinking about like how accurate is it, things like that. If we knew it diverges, we would know there's no point in trying to do that analysis. So that's basically where we end up standing on these things. I'm going to come back in the next video and finish this page, unless something goes terribly wrong, in which case, I don't know, more videos. So I will see you in the next one.